So in every redox reaction, we have an oxidizing agent and we have a reducing agent. The reducing agent is the one that gets oxidized, therefore causing reduction. So we say it's an agent of reduction. The oxidizing agent gets reduced, therefore causing oxidation. So it's an agent of oxidation. Now, what does that ultimately mean? It means that if this electrochemical reaction works, or this redox reaction works, then we should see that the electrons transfer from the reducing agent to the oxidizing agent without any extra energy. When a reaction happens naturally or without any input energy, we say that that reaction is spontaneous. And so we can measure the spontaneity of a redox reaction by looking at something called the reduction potential of each species involved. Now, the reduction potential is an arbitrary value that describes the ability of a substance to gain an electron. Not all substances gain the electron at the same capacity, and it all comes down to the electron affinity and electronegativity of the elements at hand that are involved in the chemical reaction. Substances or elements that can readily gain electrons have a high reduction potential, and we assign that high reduction potential with a positive value. Substances that are not likely going to accept electrons would have a low reduction potential, and we would assign that a negative value. Now, these positive and negative values are all with reference to hydrogen. And so if an element can readily gain an electron or electrons better than hydrogen, we give it a positive value. And if an element or a compound does not gain electrons as effectively as hydrogen does, we assign it a negative value. That being said, the standard reference to reduction potentials is hydrogen gas. Now, reduction potentials are measured in volts, which is the energy per unit charge. And you might be asking yourself, well, what does that have to do with a redox reaction in electrochemistry? If you understand where the energy is placed, it's often the energy that tells us why things move the way that they move. If we understand what low reduction potential means in terms of the energy that the electrons have, it explains why they go from the reducing agent to the oxidizing agent. Now, when a substance has a low reduction potential, that means that it's not likely going to gain any electrons, and that's because it probably has enough. And when it has enough, it's actually more likely, in fact, to release the electrons that it has. And so if it's likely to release the electrons that it has, that means that those electrons are highly energized. The thing is, what kind of energy are we talking about? Well, low reduction potentials are associated with highly kinetic electrons, meaning electrons that can move pretty well. If those electrons are energized enough, they'll be able to move effectively from the low reduction potential to the high reduction potential, or from the reducing agent to the oxidizing agent. Remember that idea in physics that energy cannot be created or destroyed, it just transforms from one form to another? Well, it's kind of the same thing here, that the kinetic energy that those highly energized electrons have, if there's not enough, they're not going to get to the top of that hill. If you think about a ball rolling up a hill, if you toss that ball very lightly, it likely won't reach the top of the hill. But if you give it enough energy, enough push force, then that ball can go up to the top. It's the same thing with these chemical reactions. The redox reactions that work or are spontaneous are the ones where the low reduction potential is low enough that the electrons have enough energy to climb up that large hill or to get to that greater reduction potential. In short, if we can prove that the oxidizing agent's reduction potential is indeed above the reduction potential of the reducing agents, then that proves that there is a hill to go down, or a rational, natural, high potential to low potential path between the two agents. So we say that if the oxidizing agent is above the reducing agent on the reduction potential table, then the reaction is spontaneous. So copper metal is placed in a solution of silver nitrate. Will the reaction be spontaneous? If so, what is the net redox reaction? So we're going to follow the 5-step method. Whenever it's a solution, I want you to understand that there's water present. Now the first thing we're going to do is we're going to list all entities including water because it says solution. So that's copper solid, water liquid. It'll be silver ions, Ag+, and then we're going to write the nitrate ion. And whenever we have ionic compounds, we're always going to break them apart because they do ionize in solution. Now, of all the entities listed in step 1, we're going to identify which are the oxidizing agents and which ones are the reducing agents. And we can do that using the data booklet. And using the data booklet, all the elements and substances on the left side of the table are the oxidizing agents, and all the elements and substances on the right side of the table are the reducing agents. Certain substances like water show up on both the left side and the right side, so they're OAs and RAs. Now this table is ordered in a particular way. When you go down the table, the reducing agents get stronger. So the strongest reducing agent would be lithium solid on the right side of the table. When you go up the table and you look to the left side, it increases in oxidation strength. So the strongest oxidizing agent is fluorine. So we can then use this table to determine, well, which of the oxidizing agents and reducing agents listed in the entities are the strongest. And all we're interested in are the strongest of each. And we'll compare the strongest oxidizing agent and the strongest reducing agent. So in this case, when I'm looking at the oxidizing agents, I have silver ions and I have water that are present. And between the two, silver ions are higher up on the left side, so they're the strongest oxidizing agent. When I look at the reducing agent side, I'm looking at whichever one on the right side is lowest. And in that case, between copper and water, copper is the strongest reducing agent, so we're going to label that as the SRA. Now, we didn't label NO3- as anything because when we look at the table, it requires H+ to count as an oxidizing agent. Once we've identified the strongest oxidizing agent and the strongest reducing agent, we're going to check and see if the strongest oxidizing agent is above the strongest reducing agent on the table. And in this case, we can see that Ag+ is above Cu solid. What that means is that this reaction is going to be spontaneous. And so it does not need any extra energy to work. If the reaction is spontaneous, we can use that data booklet or the half reactions in the data booklet to write our final redox reaction. Now, when we're writing the half reaction for the SRA, write it from right to left since it's getting oxidized. We then combine the two half reactions and balance them using the half reaction method we discussed in previous videos, and then this will be our full spontaneous redox reaction. Again, you only want to do this if the reaction is spontaneous, otherwise no reaction actually occurs. And normally in these reactions, we should be canceling out the electrons. Copper metal is placed in a solution of lead-2 nitrate. Is the reaction spontaneous? Write the reaction if it is. So, like we did previously, we're going to list all entities, and because it says solution, we're going to write H2O as well. Don't forget to split the lead-2 nitrate as it is ionic. Now, using the reduction potential table, we're going to figure out which of these entities are the strongest oxidizing agents and the strongest reducing agents. And we can see that the copper solid is the lowest on the right, and lead is highest on the left. Next, we're going to see if the reaction is spontaneous by seeing if the strongest oxidizing agent is above the strongest reducing agent. As we see here, it is not. Lead-2+ is below copper solid. So what does that mean? Well, that means that the reaction is not spontaneous. It would need extra energy input, and hence it wouldn't appear to work. And so since this reaction is not spontaneous, then there is no reaction, so there's no need to write a balanced redox reaction, and we can just leave it as is. For this last one, pause the video and try this one on your own, then unpause and see if you got it right. One key thing to remember about this process is that even if you have 10 oxidizing agents and 20 reducing agents in a single redox reaction, all we're interested in is the strongest oxidizing agent versus the strongest reducing agent, and we check the spontaneity between them. The rest are just spectator ions that are not actually present in the chemical reaction. Let's try this process in real life and see if it works.